Hi kiddos, welcome back. We are going to talk about 6.4. This is percent yield. All right, please fill in the header. We've got 6.4% yield. This is page number 8 or whatever page you might have. And the essential question is, how do you represent the accuracy of an experiment? So we're going to start off by defining a couple of words here. And then we'll just kind of jump right into it. You'll need a calculator and a periodic table for this, so have those close to us, please, so that way you don't have to go digging for them later. All right, so let's jump right in. So our vocab, we've got percent yield. Percent yield basically tells us how well an experiment went. Did it go well? Above 90% is really awesome. Even about probably 85% is good, depending on the reaction. So sometimes we're looking at it's kind of comparative, right? But like a 60% yield, probably not something that we would consider good. Probably just like grades probably would be a good way to kind of look at this, but you will never actually get 100% yield because there's always going to be some lost. Um, but we can talk about that when we do labs. Moving on to theoretical yield. Theoretical yield tells us how much we should have recovered. How much should we have gotten back if the reaction or the experiment was perfect? And then last but not least is how much did we actually recover in the lab? What did we get back? All right. What can I quantitatively measure in the lab? So this is something that has to be found in the lab. All right. This must be found in the lab, measured in the lab. All right. It could be given to you in a question like it says, they recovered this much, but for the most part, this is something that has to be figured out in the lab. So let's go ahead and jump to our formula here. So we've got our formula is percent yield. Keep it real simple. Percent yield is equal to the actual yield, like what you got, over the theoretical yield. And then we're going to multiply that by 100 because it is a percent. So this is exactly how you would calculate your grade on a test or something. You would take how many you got right over the total number possible. So you should already know how to do this. So this should be a fairly simple thing. So let's go ahead and keep working. We've got an example here. We've got mercury 2 oxide decomposes into mercury and oxygen. Let's go ahead and fill in our molar masses real quick here. So we've got HGO. Remember, that's just kind of as a quick review, we're going to take 200.59 times 1 because that's the molar mass of Hg, right? And then we've got O, we've got 15.9994 times 1, which obviously is those two things. So we're going to take 200.59 and we're going to add 15.9994. And we're going to get, and we round to 2 decimals, so we're going to get 216.59. And remember, our label on that is grams per mole. All right, so mercury is really simple because it's just 1, right? So we're just going to say 200.59 grams per mole. And again, we just found that on our periodic table. Then we have O2. This one's going to require a little bit more work. We're going to take O, we've got 2 times 15.9994, which is like 31.9988, but when we round to 2 decimals, we're going to get 32.00. So those boxes were just for us finding molar mass. So hopefully that's pretty straightforward for us. So let's actually get to the meat of the question. It now says when 1.25 grams of Hg is heated, what is the theoretical yield of mercury? So we know we have Hg and we're looking for mercury. All right, so let's go ahead and get started. We're going to put 1.25 grams of Hg. This should be HGO. Let's make that HGO. That's a mistake. It will be fixed on yours, but for mine right now, it is not fixed. But you guys, like I said, will have it fixed on yours because I haven't printed these off yet. So we're going to take this and we're going to divide by 216.59 grams of HGO. 1 mole of HGO. So we are just doing a stoichiometric line for finding the theoretical yield. So something to help you remember is you will need like a stoic line to figure out the theoretical yield. All right, continuing on. We need our multimole ratio, so we're going to say 2 moles of HGO. and 2 moles of Hg on top. Cross out moles of HgO. And last but not least, we have 1 mole of Hg, and the molar mass of Hg. Bad writing from Miss Griffith, but that's okay. We got 200.59 grams of Hg, and we're ready to do our math here. And we'll multiply across the top, divide by what's on bottom, so 1.25 times 2, but we can actually take these 2's out because they're, right, the same thing. So we're going to take 1.25 times 200.59 plus 216.59, not plus, divided by 216.59. All right, and we should get 1.15, let's say 1.16 when we round to 2 decimals, 1.16 grams of Hg. This is our theoretical yield. This is how much we should have gotten back. All right, so we're going to keep working here. Now it says if only 1.09 grams of mercury is recovered, what is the percent yield? So this is theoretical. This is my actual. And remember, our percent yield is actual over theoretical times 100. So let's go ahead and plug that in. We've got actual 1.09 divided by 1.16 times 100. 1.09 divided by 1.16 and times 100, we get 93.97. That is a pretty good reaction there, percent yield. All right, thanks. See you next time.